Hello, everybody. It's good to be here. I skipped a few years. I think last time I was here, 2014, Seattle. I see many familiar faces and some new faces. Hopefully, some younger faces in the future too. To carry the torch of the HPC leadership. Yeah, I'm going to be. Thank you, Lori, too. One thing we learned from endemic project actually, which was very similar to your project, was that those small companies, SMEs, doesn't matter if they are small, they still have big problems, So, how you actually, go along with those big problems, for a small company, that's another, avenue to talk about. So I'm going to be talking about direct solver for multiphysics modeling on our Blue Waters Petascale architecture. But since some of the previous speakers mentioned NCC industry, I'm just going to use the opportunity in a few slides actually to remind everybody about NCC industry. We are, as Bill Kramer says, for 31 years here around. We are solving industrial most demanding HPC challenges. Many sectors working with us, and we are one of the largest HPC industrial engagement in the world right now. So you can see people like to use logos. You can see the logos of our partners, and also snapshots in August 2017 of companies that we work with. You can see traditionally manufacturing is very mature area that we are working, but some other areas, middle row is technological companies, from software to hardware. And then, life sciences is an area, that's there where we see lots of growth lately. And of course, oil and gas and even financial sector, So one thing is, for example, interesting here, you see here Simulia, the salt, so once one of these companies become a partner, then you can see pretty much that other companies, ISVs in this case, who are competitors, becoming interested highly in our program, knocking on our door. So let's talk about services that we are providing. As previous speaker says, industry is coming to HPC not because of cycles only, but also because of expertise. And I have three teams actually at NCC that are reporting to me, and one is, as I mentioned, it's our strength in manufacturing, but also, we are developing expertise in bioinformatics and big data and analytics, especially deep learning, so we are building quickly expertise in those areas. Of course, computing and data, I'm going to say a few words about that too. We have a dedicated system to our industrial partners called iForge, which is aside from Blue Waters, which is the largest open science supercomputer in the world, funded by NSF. And then, except for direct partnership, we are engaging with these public-private partnerships, and some of these are under NNMI, started with the Obama's administration, so one is, for example, the digital manufacturing and design to capture data in every stage of the production and use software and digital tools to actually improve the process. And the other one is actually lately announced is AFOA, which is working to improve design and manufacturing of the smart textiles. And hopefully they can see and sense and communicate and store energy, so that's awarded to MIT. We are working with MIT, we are working with Drexel too on those projects. So as I mentioned, there is an iForge system, always on a cutting edge, latest and best HPC technologies, and also Blue Waters, which is an NSF machine from 3 years ago actually funded. So iForge, again, on a cutting edge, doesn't have as many cores as Blue Waters, but we can pretty much go through the moderate and large scale workloads with iForge, and it's built for industry, and there are no academic users on this system. So this is iForge right now, featuring Intel TikTok, so you can see we have parts of Haswell, parts of Broadwell, parts of Ivy Bridge, and we are already looking, many people mentioned Skylake, so we believe that Skylake indeed is going to be a major step forward in HPC. Blue Waters, everybody knows about Blue Waters, so what is interesting is featuring about 300,000 cores on XE6 size, and lots of also cores on GPU side. And if you are not very eager about floating point operations, and you can use actually a pair of integer processors for one FPU unit, then you can come to 600,000 cores. And I'm going to show you application actually that scale to 600,000 cores, industrial application. Okay, so now, step back from NCSA industry. So this is the quote from Professor Tom Hughes. Maybe some of you know him. He used to be president of the International Association for Computational Mechanics. He's a professor at the University of Texas. And this is an interesting quote. Actually, I was a grad student at that time, 2003, and he said, even when supercomputers become size of the football field, which is actually the case right now with blue waters, they'll be still too small and too slow, and I'm going to show you right away one of the examples. So this is the challenge from one of our industrial partners. Actually, this was at ISC 14. Dr. Jan Hu from Rolls-Royce, he said, I have a dream. And my dream is to do high-fidelity virtual engine simulation and design of one of my engines, and quick back-of-the-envelope calculations show actually for that kind of calculation, accepting multiphysics and multiscale, will take about 1 trillion degrees of freedom and 1 billion cores per calculation. So, you start thinking, where we are right now, even with exascale, we are still far away, not to mention, for example, direct numerical simulations, turbulence, So here's the list of our industrial achievements on blue waters. So it started actually pretty much with the inception of blue waters, when we started working with Cray, LSTC, which are makers of LS-DYNA, Rolls-Royce, P&G, and that kind of recipe, having our industrial partners, having Cray, which is our OEM, and having our partners actually who provide the real-world examples actually, resulted in 15,000 core scaling of LS-DYNA back in 2013. And then we move on with the CFD codes. They said, CFD codes are actually scaling better than FEA codes. So what can we do with you guys? So we started working with STAR CCM from C8 APCO, and also with ANSYS Fluent. Both codes actually went to the 6 digits. I believe now the world record actually for ANSYS Fluent is at Stuttgart, about 150,000 or close to 200,000 cores. But we provided a major step, for these guys. And then along the way, our international collaborators from Barcelona Supercomputing Center, there was a speaker from Europe. We started working with them, and they have a highly scalable code, which was meant for petascale machines, even though they started actually coding that code, multiphysics codes, in 2003. And turned out actually ALIA, with all the multiphysics that we coupled there, scaled to 100,000 cores too. And what is interesting there is actually we got 90% efficiency at that point. That's the point where Blue Water's leadership actually started twisting my arm, so I couldn't really use any more cores at that time. I'm going to be talking about WSMP, which is a direct solver from Watson, IBM. We have a couple of breakthroughs there, 65,000 cores on the CPU side, and then also 512 GPU nodes, with a direct solver. One thing I should mention, I already mentioned it, is our newest breakthrough is oil and gas, working with ExxonMobil. There was they have an in-house code that's doing flow through the porous media in their reservoir simulation, so that's the place where we actually use that double stream mode of blue waters using all the integer cores, and we ended up actually with all the cores that we have in blue waters, 700,000, more than 700,000 cores, we were able to scale up that code. Also mentioned, H3 Africa, which is a consortium for the human heredity health in Africa, some of our bio guys, they work with them, so it wasn't really about scaling, it was about high throughput computing, and they were able actually to use 600 terabytes of data, on a disk space actually to do in a high throughput computing fashion, some genomic analysis and interesting results, for some of these African nations. Okay, so let's talk about linear solvers. So why is that important? So every implicit code, doesn't matter if it's scientific or engineering, is solving some kind of linear system of equations. So that's where typical finite element and CFD code is spending 70 to 80% of the time. And when you think about applications, we have wide range of applications, coming from solids, fluids, everything coupled, geophysics, circuit design, linear programming, and etc. And even if you have a nonlinear problem, which we do, all the time in nature, very few things are linear. But if you when you're working with nonlinear things, the way we solve most of the time nonlinear problem is actually to do the linearization and solving actually a bunch of linear systems all the time, and that's what we call Newton-Raphson iteration. So, what is problem with that global stiffness matrix, that we have to solve is, besides being very sparse, it's very ill conditioned. So there are few very common actually reasons why the matrix is ill conditioned. And in my research, actually, I encounter all these cases. For example, so what you see on the left side is a trabecular bone, so we are working with Mayo Clinic and doing micro-CT of the trabecular bone, and the only way actually to discretize, to mesh that kind of beast is actually to use tetrahedral elements, and you ended up actually with very high aspect ratio elements, so that's first of the reasons why we have ill conditioning of the global stiffness matrix. And then if you have some kind of loose boundary conditions, for example, friction on this part of this structure, which is providing enough statical resistance, but at some point resistance frictional resistance is overcome, and the part starts moving. That's where the global stiffness metrics become sort of singular and ill conditioned. And then coupled multiphysics with highly different material properties. Part of my research interests are continuous casting, and when you start continuous casting, actually you start with the liquid, turbulent liquid, you ended up with the solid. And when you look at these properties, the liquid part has totally different properties than the solid part. So once you start coupling these things in multiphysics fashion, ended up with the global stiffness matrix, very ill conditioned. And I'm just giving you an example here, so small deviation in these entries, can give you totally different results, So what the people do, so essentially we have two kinds of solvers. We have iterative solvers and direct solvers, and traditionally, when you open any textbooks, you're going to find that for big problems, people are using iterative solvers because, they are using less memory and they are also better scaling. So they, repeatedly apply sequence of operations and on each step improving its current approximation to a solution. So this is all great unless you have a ill-conditioned problem. If you have ill-conditioned problem, the only way actually to solve it is to use direct solver. And in direct solvers, we are doing some kind of factorization of the matrix. Ended up with L part, which is lower part, and U part, which is upper part. If you have a symmetric matrix, then you have L and transpose of L, and then we use Cholesky factorization. So I'm going to be comparing some of these solvers soon. So the solver that's turned out to be actually, I have been working with Watson IBM for many years, and every NCSA system that we have, it was solving extremely well. So the good news was actually in 2012 when we got Blue Waters, project and machine. Interesting thing was right away, how well WSP Solver is going to scale on Blue Waters. And just, to give you synopsis here, what Watson is doing, what WSP is doing, basically is collecting columns with a similar non-zero pattern, trying to make a dense part of these matrices, and then using blast tree operations to do this efficiently as much as possible. Nobody is really operating on zeros. And for these small matrix parts which are dense, if you can do the hybrid implementation actually with some kind of threads, P threads in this case, or GPU threads, then you can give even better scaling. So here are the test problems from real world problems actually. So you can see test matrices from 2 million degrees of freedom, 2 million unknowns to 40, all the way to 40 million. This M11 is actually high yield condition, so you can see the condition number, going to the 10 to the 9. And then from geophysics, we also have, we work with Barcelona Supercomputing Center, as I said, and their partner Repsol was actually providing these geophysics matrices, and some of them are really ill-conditioned too. So this is the earlier work we did on iForge. So we were comparing PETC and Hyper and one iterative solver, ABF, so-called adaptive black factorization sparse solver with nested incomplete Cholesky from Padua, Italy, and then against WSP. So you can see from the total solution time that iterative solvers were outperformed by WSP and IBF. But when we went to high yield condition problem M11 that had the highest condition number, only direct solvers could solve it. You can see two typical direct solvers like MUMPS from France and WSP, while WSP was really scaling much better than MUMPS. So this is the work we did on blue waters. You can see that WSP on blue waters with these multiphysics test matrices actually scaled all the way to 65,000 cores with the largest problem, M40, and did very well actually with M11, which is high yield conditioned. And in terms of teraflop rate, we got about 70, 80 teraflops in that case, which was a really good result for sparse linear algebra. One lecture we learned was that you can see on the left-hand side, actually, my colleagues from Blue Waters, they captured the total interconnect traffic through Gemini, through our interconnect, during the execution, and you can see, how the communication becomes on a larger scale very, very important. So the one important lecture is actually, doesn't matter if it's direct solver or iterative solver, communication becomes much more important than communication. So communication becomes much more important than computation. So you have to have a really good interconnect actually to go to thousands of cores level. And the other one was again, traditionally we were saying direct solvers, using so much memory. So during the factorization, you can see that going from M40 to M20, M11, as we are scaling wider on more and more nodes, the average memory consumption dropped significantly. So we can certainly solve even better problems, bigger problems than M40, on blue waters. So here's another problem set from geophysics. So they do so-called inversion. So they send electromagnetic waves, and they got data, and they are trying to produce these images where they can see where the oil is. And if a oil company is failing, it can cost actually that company millions of dollars, if they are digging somewhere where they are not supposed to dig. And traditional iterative solvers are gain, and these are complex numbers. So you have imaginary and real parts. So the storage becomes even more of the issues. And turn out actually that direct solvers, according to Repsol and according to my colleague from Barcelona, gave really clear pictures, for these problems. And they are along the way, actually, this is pretty new, so they are considering actually to use direct solvers in their future research. So what is interesting here is these geophysics problems, they gave even more performance and better scaling. So you can see the largest problem size called M5 scale also to 65,000 cores, but the performance was almost 100 teraflops, so here you go, 0.1 teraflops, 0.1 petaflops actually on a sparse linear algebra is a really good result. And then along the way, we ported also work with NVIDIA, and I wasn't directly involved with this part, but the idea was actually to use GPUs instead of threads, and so minimally invasive approach was taken here, so the host pin buffers were help actually to overcome some of the problems with GPU, especially running through the PCI. And you can see, that the pretty good results actually were achieved on GPUs. Best to our knowledge, this is the best scaling with direct solvers, on 512 GPU nodes in the world so far. So we can see some of the ideal lines too. So at some point, of course, the traffic between the host and the GPU memory is going to kill you. But up to 512, you can see the benefit of actually running on a GPU versus just CPUs. Okay, so coming slowly to conclusion, I'm almost done with my time. Direct multifrontal factorization like the one in WSMP performed beyond the expectation, exceedingly well actually on a Petascale HPC system. The two major problems, two major concerns, about memory scales for factorization and also communication, are turn out to be actually still issues, but the memory scales very well. And important lecture is if you're going to be running multiphysics or multi-scale applications on a petascale level, you better have a good interconnect. We are working with Barcelona Supercomputing Centers in implementing actually WSMP as a direct solver and also as a preconditioner, into ALIA that I mentioned in a multiphysics code that right now has only iterative solvers. These so far were all symmetric problems, so if you are doing Steve, I have one more. So if you are doing fluid structure interface, for example, you have advection terms in fluid flow, then you are actually ended up with non-symmetric systems. And good news is actually WSMP from IBM Watson, they also have non-symmetrical solvers. And we believe, as the size, speed, and availability of many cores, multi-core accelerators, and so on, in sub-exascale and exascale era becomes more and more available, the usage of these direct solvers will be more and more, so the usage will grow. We also hope, this pioneer work in scaling direct solver on Petascale architecture will lead to significant, jump in terms of advances in high fidelity modeling and design in both science and engineering. One thing I would mention, we are also organizing the NCC Industry Annual Meeting at University of Illinois, October 11 and 12. And our partners said, they want a more opportunity to network, collaborate, and share about HPC this year. So we are planning to hear from our partners and our domain experts together, this year, talking about results and how they address challenges of all scales. For more information about our NCC Industry Annual Meeting, a new director of NCC Industry, Brendan McGinty, is here. Brendan, can you wave so people can see you in here? Okay, so that'll be all. Thank you.